Okay, today we are learning about differential geometry. Here is question number 1 related to MCQs. If one parameterization of a curve is regular, then all other parameters are always regular, never regular, may or may not regular, or none of these. So its option is may or may not regular. For assistance, we can get an example of parabola y is equal to x square, which have parameterization curves gamma of t comma t square, and second one is this, and third one is t cube comma t power 6. Here we can see that first curve is regular because first derivative will be this 1 comma 2 multiplied by t, and if we put any of the point, we can't get 0 comma 0 order pair. So by definition of regular curve, that is regular. And if gamma of t is equal to 2t comma 4t square, then it is also regular because when we take derivative, here we have x component constant, which will never 0 for any given point. So that is also regular. But if we can observe the third example, t cube comma t6, it's not regular because when we take the derivative, there is a function depend upon t, and we can put t is equal to 0 and get 0 comma 0. So at t is equal to 0, that curve is not regular. Now the question number 2, which is also an MCQs. Which of the following is singular point of gamma of t comma t cube comma t6? So if we want to take the singular point, just like this question before, we just take derivative and put that derivative is equal to 0 comma 0. So from comparing, we can see that value of t will be 0. Now the next topic is related to equation of straight line in space. We already discussed here. Space means 3 dimension, which have x-axis, y-axis and z-axis. So equation of straight line in space have different forms: vector form, parametric form and symmetric form. Firstly, we can see the vector form. Equation of straight line through a point A and parallel to vector B is given by, here is a position vector R, which is equal to A plus TB. T is basically a constant multiple of this parallel vector B. So R is equal to A plus TB. So equation of straight line, you can see that R is equal to A plus TB. And equation of straight line through point A1 and A2. If there are 2 points, then we can observe that this B is replaced with the difference of second minus first, A2 minus A1 points. Other are same. First function is A, here is A1. Next one is parametric form of straight line in a space. So equation of straight line through point, this is a 3-dimensional point A1, A2, A3 and parallel to vector B, B1, B2, B3 in ijk component. We can observe that in parametric form we can write up x, y, z in different form, and similar to that equation of straight line through a point, we can put here vector A replaced with A1 and vector B replaced with B1. For y component A2, B2 and for z component A3, B3. So in that pattern, next is the symmetric form. So equation of straight line through point A1, A2, A3 and parallel to vector this. Again rearranging this, for example, we can do that A1 is shifted left side, and here is t, and the fraction goes to B1. So that is called the symmetric form. Here is for 1 point, x minus A1 over B1 is equal to y minus A2 over B2, z minus A3 over B3. And if there are 2 points just like this, a1 a2 a3 and b1 b2 b3, then we can do that. We can differentiate, take a difference b1 minus a1, b1 minus a1. Only do that from second component we minus first component in fraction instead of vector b. So that is the replacement. Next we can see the equation of straight line in a plane. So in xy plane we have just two variable x and y. So ax plus by is equal to some constant c. Now the next topic is related to equation of planes in vector form, as well as one point form, as well as in general form. So equation of planes, let's see a plane containing point A and a normal vector n is a normal vector to plane. Then for any point P of R on the plane, here n is perpendicular to AP. AP is basically the distance of 2 points in vector form. Okay, so n is perpendicular to AP. Then we know that inner product or dot product of a perpendicular vector is 0, and if we put values of AP, we can see that r minus a vector. So that is the equation of plane in vector form. And if we want to write up in one point form, so again for a plane containing this and normal vector this to the plane, then for any point P of xyz on the plane, equation of plane is, we just do that this is a dot product, and if we write in component form, so as n is component form n1i, n2j, n3k, and in component form r minus a is x minus a, y minus a2, z minus a3. So we can write in the linear combination of this equal to 0. So this is the expansion of this dot product. Again, the general form of the planes in vector form is related to ax plus by. It is a basically space is related to r3. Here is x, y and z. There are 3 coordinates. Okay, next is a unit vector along the tangent to given curve is given by. As you know that unit vector is the vector whose magnitude is 1 and the tangent to a given curve. So if the curve is r, if we take the derivative of this curve with respect to arc, s is related to arc. Here s is a arc, and we can take differential of this curve with respect to arc. We can find the unit tangent vector. So hope so you can understand. Next is a tangent line at a point on a given curve. So for tangent line we can do similar to equation of straight line as we done here. From position vector we replace capital R is equal to small r plus u is some constant which is multiple of this tangent vector t, unit tangent vector t. So next is about tangent line when equation of curve is given as intersection of two surfaces. When two surfaces interact, there is an intersection and we can find some plane. So tangent line when equation of curve is given as intersection of two surfaces. So there is a first surface, there is a second surface. When the intersection happened, then after that first derivative of x, first derivative of y and first derivative of z, they are equal, and we can replace, we can write up in denominator partial f1 over partial y, partial f2 over partial z. If there is an x in a derivative in numerator, then there is no term of x, only f1 with y, f2 with z, minus f1 with respect to z and f2 derivative with respect to y. So for y there is no y, we again take f1 with z, f2 with x, minus f1 with x, f2 with z. Again for derivative of z, we take the denominator f1 f2, f1 f2. Here is a partial x partial y and partial y partial x. So we need only to observe the denominator derivative with respect to some function. So if there is an x, we can see yz zy. If there is a y, we can see zx xz. If there is a z, we can see xy yx. So it's just like a cycle. Here is an x, y and z. So in first case, if there is an x, we move toward yz and minus zy. And if there is a y, we can move toward zx and xz. And if there is a z, we can move x to y and y to x. So to remember this, we can just do that pattern. Now there is an arc length of a curve. Let P be a point on the curve and R is that curve, A be a fixed point and AP is a arc. This AP is equal to S, which is arc. Then the unit vector along the tangent is given by, we have to do that if we know the previous result, unit tangent vector is equal to dr by ds, derivative with respect to arc. If we can take mod, then that will be equal to this, and unit tangent is equal to 1 dr over ds arc length, and magnitude of arc length is again ds. So cross multiplication, we get ds is equal to dr modulus, and here is an integration s, and as we can take the point a be a fixed point and ap is equal to s, so we can do that a to t is the integral dr modulus, and for our assistance, because we are integrating with respect to t, dr over dt mod is equal to dt, dr by dt is equal to r derivative. Here we can use the symbol of dot for derivative, because that derivative is related to other than arc. Dr by dt we can represent from this, and this is for dr by ds. So in Cartesian coordinate, if we want to find the answer of this, we can know that r is equal to xi plus yj plus zk. So dx over dt square plus dy over dt square plus dz over dt square, dt as it is, and square root we can take the whole term. And after that we can observe that always if we want to find the arc length, we have a limit from initial to final a to t, because t is variable. We can write in short form, in closed form, dx over dt x dot square plus y dot square plus z dot square is equal into dt. So here is a note which I already said here. Derivative of r with respect to s denoted by r prime, and with respect to any other parameter we can use r dot. So there is an arc length in Cartesian coordinate, parametric form, and polar coordinates. There are three forms to write the arc length. In Cartesian coordinate, s is the arc length of the curve y is equal to fx from the point a x naught y naught to the point p x y. Then first initial point is this and final point is this, so that s is equal to x naught to x 1 plus, here we can take derivative dy over dx and whole square root d of x. So that is the formula if we want to find the arc in Cartesian form. And if in parametric form where variable is t or any other alphabet, we just do that from t is equal to t naught to t is equal to t1. Only parameter is t, so t naught to t1 square root of dx with respect to t and dy with respect to t, and square taking the sum of these two derivative square sum, we get the answer of the arc. Also for polar coordinates, s is the arc length, r is a function of theta, here is an angle theta naught to theta 1. We can start from theta naught and end at theta 1, integrate r square plus dr over d theta square with respect to d theta. So after that, if we put the values after finding r and dr by d theta, we get the arc length in polar coordinates. Now let's see how to apply these formula to find arc length of any curve. Here is a question number 1. Find arc length of r which is depending upon t. T is from 0 to 1. First we need to find the derivative with respect to t. Here is a derivative. Then we can find the arc length which is from 0 to 1. And we know the formula of arc length for parametric coordinates, parametric form. So x dot square plus y dot square root dt. We just put the values from this because coefficient of this x is 1 and this is 2. So for that reason 1 square is equal to 1 and 2 is equal to 4t square. And after taking common we can do this, and after that 1 over 4 becomes common term, and integration of this whole function is equal to t by 2. As you know, the formula is if there is a square plus t square square root, we can integrate. After integration we get t by 2 square root of a square plus t square, same as it is, plus a square over 2 some constant a square over 2 natural log of again t plus a square plus t square. So apply here 1 over 8 square 1 over 4 t by 2. T by 2 is basically this, and 1 over 4 plus t square means this is equal to 1 over 2 square plus t square. So after integrating we just observe that is the after applying limit answer. And after applying limit we have the simplifications, we have some natural log laws, and after that we can get this is the answer. Now the question number 2, which is equal to this, and limit from 0 to pi. This function is also depending upon t, so it is a parametric form. We know the formula for parametric form, we need derivative. After derivative we have a component of x, y and z. We can take the derivative squares, and after that we can get this after simplifying. Here is a formula of 1 plus sine hyperbolic square 2t is equal to cos hyperbolic square 2t. So this one and that one will become 2. After integrating we can see that the answer will be 3 into square root of 2 sine hyperbolic 2 pi. So next we need to discuss about normal plane. Let P be a point on the curve, then plane through P orthogonal to tangent at P is called normal plane at P. So remember that normal plane is always orthogonal or perpendicular to tangent. Equation of normal plane we can find. Let that is the curve, and be the position vector of point P, and r be the position vector of any point on the plane. Then r minus r lies in the normal plane. That normal plane is perpendicular to tangent, so normal plane dot tangent dot product will become 0. So we know that tangent is equal to derivative of curve or position vector with respect to x, and tangent is again derivative, so it's a only derivative, sorry, it's a single derivative. So this is equal to 0. We can observe this from that figure. That is a plane, and normal is perpendicular to this. This is basically tangent, okay, and this is a normal plane which is perpendicular to tangent, that is 90-degree angle. So we can remember that note r prime is equal to dr by ds is a unit tangent vector, and if we can take the derivative of this position vector dr by dt is also a tangent vector. This is also a tangent vector, but not necessarily a unit vector, but it is not a necessarily unit vector. Here we can solve the example of a normal plane. Here is a position vector r at t is equal to 1. So we need to find normal plane at point 1. We can take the value at 1, and after taking derivative we again find value of derivative at 1. So we also know the formula. After applying the formula, we put the values. R is equal to x, y, z, and small r is equal to, we know that t comma t square t cube. So their components is 1 1 1, because we are taking at t is equal to 1, and t is equal to 1 is this, and derivative is equal to this. We can put the values and see that that is called the equation of normal plane. Equation of a normal plane. Now the most important topic related to curvature, and the curvature of a curve at any point is the rate of bending of the curve. The curve, how much bend and what is the rate of bending. The rate at which the tangent at any point P is turning as the point of contact P moves along the curve. So curvature is represented by K, which is equal to kappa is equal to theta prime, and we know the limit delta s approaches to 0, delta theta or delta s becomes d theta by ds. So kappa is equal to d theta by ds. Curvature in vector form, the arc rate at which the tangent vector changes direction as the point P moves along the curve is called the curvature vector and is denoted by K. So K is equal to tangent vector dt by ds, derivative of tangent vector dt by ds. Now there is its magnitude K is equal to K mod, which is called curvature at point P. Here are some notes. Remember that K is orthogonal perpendicular to T, because we can take the derivative of tangent. So K is orthogonal or perpendicular to T, and then we can also said that K is parallel to normal plane. So K is in the direction in which the curve is turning. Kappa is in the direction in which the curve is turning. Since T is equal to first derivative of position vector or curve, so kappa is equal to second derivative of r or curve with respect to s. Then if we want to find the mod of kappa, then we need to find the modulus of r double prime. So curvature is also in Cartesian coordinate, parametric form, implicit form, polar coordinates. So one by one we discuss that. Curvature of a curve y is equal to fx, which depend upon x. Kappa is equal to second derivative with respect to x divided by 1 plus first derivative with respect to x square and whole power 3 by 2. And parametric form, curvature of the curve x is equal to f of t, y is equal to g of t at point P of x, y is equal to kappa is equal to division. Here we can see that first derivative of f and second derivative of t minus first derivative of g and second derivative of f double prime, f divided by sum of square of first derivative of f and g whole power again 3 by 2. Implicit form is also a very important form. Curvature of curve f of xy is equal to 0. That is called implicit form. We can do that kappa is equal to f double prime x fy whole square minus 2 fxy fx fy plus f double y fx square. So we can observe that here is a second derivative of x, here is second derivative of y, here is first derivative of y square, here is first derivative of x f at x square, and there is a difference of 2 times fxy and individually fx into fy, and fraction is same as before, first derivative square plus first derivative with respect to y square whole power 3 by 2. So fraction is in short same, but in numerator we need to some produce pattern. Polar coordinates, curvature of curve r depend upon theta, point is the p of xy. So kappa k is equal to curvature is equal to r square plus 2r prime square minus r into r double prime over r square plus r prime square whole power 3 by 2. So we need to remember these formulas if we want to do the questions related to that one. After that we discuss about radius of curvature. So radius of curvature is related to reciprocal of curvature of a curve at a point. Rho is equal to 1 over kappa. Here rho is equal to radius of curvature which depend upon curvature. So if we take reciprocal of curvature, we can find the radius of curvature. Here are some terms which are related to radius of curvature. First one is point of inflection is a point on the curve where the curvature is 0. Where the curvature is 0 means k is equal to 0, or the radius of curvature is infinite, or if we can say that rho is equal to 1 over k and 1 over 0 is equal to undefined, so it will become infinite. Next one is some theorems. A curve is straight line if and only if its curvature at any point is 0. For straight line curvature is 0, and for a circle k is equal to constant. Remember that these are very important formulas, and that is the last questions, how to find the curvature. So remember that we have given a curve r is equal to u comma u square comma u. We just do the derivative, means find the unit tangent vector. So we need to apply here chain rule, because dr over ds we can find dr by ds, but r is a function of u, so du by ds. So after applying chain rule, we can find the xyz component is equal to this, and du by ds is a common from this and this term. Unit tangent 1 is equal to this modulus is equal to this du by ds. Du by ds is equal to 1 over square root of 2 plus 4u square, and if we observe that r prime is equal to this function, r prime is equal to in component form this, we need to find the second derivative, because second derivative is the need of the finding curvature. So find second derivative and take modulus. If we can take modulus, then we know that scaling, after scaling we can see that LCM is same as 16 plus 16, 32 u square, and 16 is this one. And after simplifying u, we can observe that there is a function like this, square root of 8 over 2 plus u square, because one thing is cancel out, as we can observe that same 16 is equal to 8, this is equal to 8, and 8 2 times 16, and plus 8 4 times 32 u square. So first this will cancel out for this, and after that 8 over 2 plus u square, and after simplifying we can get the required answer. So hope so you can understand, because that is the point which we need to discuss. Here is 16 plus 32 u square, and after taking 8 common, we have same terms in numerator just like in denominator. So here is power 3, one power is cancel out, here is square and square root cancel out, and after simplifying we can see that that is the required answer. Hope so you can understand, and keep watching my YouTube channel for more videos, and moreover we can discuss differential geometry next topic in next video. Thank you so much. Allah Hafiz.